All right. Today, what I wanted to do to get started, so I want to do several things. Excuse me. I wanted to go through this list of learning objectives that I have in Lab 2. Of course, these are the general learning objectives at this stage in the course. If you look in your book, you'll see that these learning objectives line up directly with your reading. These are listed in your book as learning objectives. And what I wanted to do is just go through the list and make sure that I covered everything. Once again, this is covered in the book, and in most books. Most of the books in this subject are very similar. So let's go through this list. Understand the notion of a data type. So a data type, that's when you're storing data, representing data with computer memory, you have different types of data. You can have floating point values that have fractional components, or you can have integer values, or you can have strings, or Boolean values, values that are true or false. And those are the data types that we've been exposed to so far. Those are the main data types. Let me go into Lab 2 here. So here's an example of a data type, double. So this is a declaration of a variable called x. It has the type of double. If we had changed that to int, we would have a different data type. That's an integer value. And we could call it a bool. It's a Boolean value. Now it's true or false. So these are called data types. Now there's something called a complex data type versus primitive. So the bool, int, double, those are primitive data types. An example of a complex data type would be a string. In complex data types, you get some additional syntax that you can use with complex data types. Basically, a complex data type has a set of operations associated with it that you invoke through something called the dot operator. So there's a variable x set to the string hello. And x is a complex data type, and it has some functionality that you access with the dot operator. And one is size. So I use this period here, following the variable name, followed by the function that I want to call. Let's see that work. So the size is 5. That's a little hard to see. So I'll print a new line character there. That's a little easier. So the size of this string is 5. It's got 5 characters. Let's look at a function that's available on strings. There is a substring. So what we want to do, let's extract the letters ELL. H is in the first position of the string. That's position 0. So position labels start at 0, normally, in most languages. And the second position is position 1. So with the substring, the first argument to substring is the position to start the substring that you want. So we want to extract a substring ELLO. And then the second argument is either one of two things. It's either the length of the substring or it's the second index that terminates the end of the substring. I think in C++, and it's different in different languages, Java, C#, JavaScript, they vary in their conventions. So there's not a single convention that's used across languages. You just have to remember what language you're working in, what's their convention that they're using. And but I don't always trust my memory. My memory is that in C++, we give the number of characters in the substring as a second argument. But let's test that to see if that's true. So if it wasn't, if 3 represented an index, then that index of 3 would be, let's see, 0, 1, 2, 3. It would be the same thing, wouldn't it? So this is not actually a good example. Let's try extracting LL. So we're going to go from position 2, which is the third position, the third character. We want to extract 2 characters. So this is position 0, right there, the H. E is at position 1. The first L is position 2. This is the first position. And then I hypothesize from my memory that the second argument means the number of characters to extract. So starting at position 2, extract 2 characters. So that would be LL. Let's see if I got it right. That is, I got it right. In another language, and it may be JavaScript, I'm not sure. This would be 0, 1, 2, 3, 4. This would be the index, not of the last character that you want, but of the character that you don't want. So this would be 1 past the position you're interested in. Anyway, these are 2 examples of operations that are available to string. And I bring this up because it's an example of complex data types. String is a complex data type. We do not have similar expressions for integers. We can't do, there's nothing like this. That won't exist. This doesn't work. So the primitive data types do not have functionality, or operations that are accessible through this dot operator. Only the complex data types. And in, I believe it's chapter 5 on classes, that's when we start to define our own complex data types. Another word for a complex data type is class. A class is a data type that you define as a programmer, and then you create instances of your class, instances of your data type. So we'll look at that very soon, a couple of weeks. How to use the string data type. We were just looking at that. And how about in one thing I want to show you about the string data type is how to concatenate onto a string. So we have this hello, word hello, and let's suppose we want to concatenate the word, the name Bob. So it's hello Bob. So we'll use this operator, plus equals. That's the same as the following operation, x equals x plus. These would be equivalent. And let's add a space. So hello Bob, say it like that. I'll make this uppercase H. We'll test this one first. So this takes this string x, which is originally set to the string hello, and then appends onto it a space, and then the name Bob, and then a period. Oh, what did I do? Oh.
You didn't see off the statement.
Yeah, that was, sorry. I just want this. I just want to print x. So this is called string concatenation, and it's equivalent to this. So take what's in x. This is not numeric addition now. This means something else. This means string concatenation. So these operators are, the meaning of operators in C++ is dependent on the context in which they're used. So here we have this operator has two operands, the left-hand operand, the right-hand operand. Those two things, they're not added arithmetically, they're just appended. So it's called a string append. So we take what's in x, append this string, Bob, and then store it into x. All right. How to change the state of a variable using the assignment operator. I think that's pretty straightforward. This is the assignment operator here. Here we declare a variable x, initialize it to 8. This is called initialization. And then in the next statement, we assign a different value to x. X is on the left-hand side of the assignment operator. And we're assigned the result of this expression. So the expression is take what's in x, doesn't have to be x, could be something else. Add 2 to it, and then store it back into x. So we would get obviously 10 for that. There's a shorthand form of this expression. We can write it like that. That's a different form of the assignment operator. It's a different type of assignment operator. Take what's on the right-hand side and add it into the left-hand operand. So x is currently 8. We're going to change its value by adding 2 to it. So then once again we get 10. It's the same thing. Same thing with subtraction. Same thing with multiplication. All the operands we can use in this form. What gets printed here? 16, that's right. What gets printed here? 4. These are all different forms of the assignment operator. Persistent. It's not pure assignment. It's, there's also, I guess you can call it assignment. It's an assignment operator. Using parentheses to form expressions. It's the same as in math. We can set x can be 8 plus 2 times 2. We do the multiplication first because it has higher precedence than addition. So this would give us 12. But if we want to change the order of operations, we use parentheses. Do the addition first, then followed by the multiplication. (20). 8 plus 2 is done first, then the multiplication. So what about the keyword const? This is something I haven't talked about yet, but you see it a lot. Suppose we want to replace this with some constant value. Say, we'll call it the factor. I use uppercase letters. Many programmers, by convention, use all uppercase letters for constants. I'll just show you that convention here. So this will give us 30. Oops, I need a note. Thank you. Yeah, I see that. Thank you. 30. Now we'll get the same behavior like this. Oops, I need to compile it. We get the same behavior, so why bother with the const? Well, the const gives us, it's like a guard against logical errors. As the program gets more complex, const is a reminder to the person working with the code that this symbol, factor, represents a value that should not change. And so if we try to do something like this, we want to change the value of factor to 2 before we use it here, the compiler will refuse to do that because we have declared the variable as constant or const. See, there it is. Read-only variable. Error. So, of course, if we remove const, we won't have that trouble. No problem. 20. But the original intent of the programmer was for factor to remain constant. And so, as the program grows, maybe 3 years later, someone is adding functionality to it, and the person gets to this point in the program where it says, oh, I need to change this factor. Let me just go ahead and change it right here. But the program has 100,000 lines in it. And so I don't have time to check all the places where factor is used. I'm just going to change it here. And if const was not used, then factor ends up getting changed to 2, and that causes bugs in other parts of the system. Remember, 100,000 lines of code. It's a sort of a normal sized program. So that creates a problem. So to avoid that, we declare factor early on as constant. So when when that programmer 3 years later tries to solve a problem by modifying factor, then the problem is discovered, and then he or she goes up here and says, "Oh, this is const. I better not change its value." Something like that. That's the idea. And how to use the complex data type string, we looked at that. How to invoke or call functions. There's two ways to invoke functions. One way is to invoke functions that are defined for complex data types. Like if x were a string, then we invoke a function using the dot notation. The name of the function follows the dot, which follows the variable name. Another way to invoke a function is to pass in an argument. So here we're calling the time function, we're passing in 0. So this gives us the number of seconds from some epoch. And then we invoke the sran function and passing in that seed value like that. So here's an example. We're invoking two different functions. So this is a different style. This is the function invoked on complex data types with dot notation. This is where we're invoking what's called a global function. It's not a function that's associated with any object instance. It's not associated with an instance of a complex data type. It's just a function. You pass stuff in, you get something out. Or in this case, you pass stuff in, and it changes the internal state of your execution environment. It seeds the random number generator, so it doesn't return anything. So here, time, this function here, when we pass in a 0, and time runs internally. We don't know the details. It's a black box. But ultimately, the function returns a value. That means, when I say the function returns a value, I mean the expression that uses the function name followed by parentheses, followed by the argument list. This expression is evaluated to its return value. So you can think of it as what I have highlighted right there, that is simply replaced by what it returns. If time 0 is 1,000, then this expression evaluates to 1,000. And then that value is then assigned into seed through this assignment operator. The seed becomes 1,000. And in the next function, sran, that we're calling, passing in 1,000, or whatever seed happens to be equivalent to when we call the function. And the function functions like a black box, does something internally. It seeds this random number generator. So it stores the seed somewhere, it does something, it changes the internal state of your execution environment. Then the function returns, but it doesn't return something that we store. So we don't say, we don't declare a variable to store its return value. We don't do that because the function does not have a return value. We call it a void function. F-O-I-D. F-O-I-D is void. It's void of a return value. It's void of it doesn't evaluate to anything. So you cannot use it in an expression that it cannot be used within an expression that's expecting a value. Now that time, let's see, do I need to, yeah, I can run that. There we go. And what about the Boolean data type? And we looked at this last time, actually, and I'm going to go over that right now. Another data type is called bool, which is short for Boolean. And bool is the name of a mathematician who developed the mathematics related to handling logical values and logical expressions. So let's declare this Boolean value b, initialize it to, say, true. So Boolean values can be set to true or false. You only have two states. Let's see what it does here. I'm not sure what it's going to print. Prints 1. We set b to true. In other languages like Java, C#, this operation would print the word true. But this C++ is an old language. No new language would do what C++ is doing for us. Internally, it stores Boolean values as integers. And the value 0 represents false. All other possible integer values represent true. So when we set b to true, here, the compiler is generating code that assigns a 1 into memory to represent true. It could have assigned 2. That would work as true as well. Let's see if it'll take this. Maybe the compiler will complain about that. It doesn't. See, look, it still shows it as a 1. You see that? Look at that. Just to show you, I'm going to write that. I save the file, compile it. Still shows a 1. We assigned a 2 into b. And then we print b and we print a 1. But really, you know, it's an old language, so you have to think about this stuff. It's based on C. Any value that's non-zero is interpreted as true. We use these Boolean values in Boolean expressions. For instance, if b is true, then print b is true. Else, print b is false. This is how we should think about it. You assign 2 to b, we're going to print b is true. B is true. If we assign I'll assign 0 to b. If we assign 0 to b, what's it going to print?
C is false.
B is false. There we go. Suppose we assign -1 to b. What does this print? Not as sure about this one, right? What do you think this should print, based on what I've said? Anybody going to say?
False.
Only 0 is false. B is true. Got that? Only 0 is false. All other values, including negative values, are true. And here's another way to do this. We see this if statement here takes an expression that evaluates to true or false. We don't need B equal to equal true, just this. If B, see? Because if is expecting an expression evaluates a true or false. So if B evaluates a true, then this is good enough. But this is generally what programmers will do. They won't say if B equals false. They won't normally write that. I'm just writing it that way so the new programmers in this class can grasp it more easily. Of course, this is not good code. You know, we should do this. This is better code. If we want that to be true, we just use the word true there, the keyword true. This is much more readable, obviously. I'm just showing you some of the subtleties of the language. In the other languages like Java, C#, and so on, you wouldn't be able to assign -1 to B. So it's not a good idea. People in general feel it's not a good idea to allow that to happen in a language. Now in JavaScript, you can assign -1 to B, and it will be true. B is true. See, if B. How about let's see, what is I'm going to cover here? How about another variable A, and A is false, and B is false. No, let's say B is true. So how about I want to write the statement if A is true or B is true. If A or B, how do we write that? If A or B. If either Boolean value is true, then I want to print it's true, say. I heard someone say that. What's the answer?
Double bars.
Yeah, that's right, double bars. This is the symbol for logical OR. There's another symbol, which is a single bar. That's arithmetic OR. And you want to be careful, don't use that. Or bitwise OR, rather. It's called bitwise OR. It just goes across a string of bits and does an OR operation and gets the result. So we don't want that. We want what's called logical OR. In this class, we won't use the bitwise operations, but we will use the logical operations. So if A or B, if either one is true, then it's true. We're going to print it's true. So here we should print true because B is true. How about declare another variable C, and let's set it to false. Look at this expression. If A or B and C, then print it's true. Or print it's false. So what does this print?
False.
Good, this prints false. And look, these are two different operations. How do you figure this out? In other words, this expression evaluates to false. How do you figure this out?
And have higher precedence.
Exactly. Logical AND has higher precedence than logical OR. So the first thing we do is we compute B and C. B is true, C is false. So they're not both true. So true and false produces false. So B and C produces false. And A is false, so this logical OR, the left-hand side of this logical OR is false, and the right-hand side of the logical OR is also false. So false or false, that produces false. You know, it's just a warning. It's warning us it doesn't like this. We can actually turn that off. How do I turn that off? Logical. I can't remember. How do I turn that warning off? How can I turn that warning off? Yeah, I saw this the other day. Here it is. With no logical. So that's to turn that off. No logical op parentheses. So now I turned off the compiler warning. You see that? Let me show that again. If I just compile this, it gives me not an error, it gives me a warning. And then it says that you're mixing and with or, and place parentheses around the ampersand expression to be explicit about what you're doing rather than relying on the default. And that will suppress the warning. But another way to suppress the warning is to tell the compiler, I don't want that warning, so I'm going to suppress that warning in particular. And so that's another way to suppress the warning. There's another way. I think you can go no warnings. I don't remember. You can suppress all warnings. Did you mean no warnings with a hash? That didn't work either. But anyway, it's false. There's the result. So the compiler, where that warning is enabled, is asking us to do this if we want to avoid the warning. So be explicit about this. They're just imposing that on us. So watch. This avoids the warning. Now I'm going to take that out. To me, that's easier to read, but that's just me. Apparently, the compiler writers have a different opinion. All right, let's look at some other expressions. What about we change A to true. Well, I'm going to show you something pretty sophisticated here in a second. So if A is true, then it doesn't matter what this is. This is always true, right? The first operand of an OR is true. It doesn't matter what's in the right-hand side. Let me do this. I'm going to create a kind of an artificial example here. Let's set I to 0. Excuse me. And let's dump the value of I. This is really a contrived example, but I want to point something out that's very important. My ear keeps getting clogged. I'm having a hard time talking. It's like clogging and unclogging. All right, so here's our expression. Oh, that's a 1, isn't it? So here is, we declare a Boolean variable a, set it to true for now. Declare an integer I, set it to 0 for now. And then we have this expression, a or plus plus I. Let's set this false to begin with. Okay? So a is false. Plus plus I is, well, I is 0, so I becomes 1. And then 1 is used in the expression. And 1 is interpreted as true. So this expression should be true. Is that right? So it'll print it's true. And then we will print what? I equals 1. There it is. What about this? I plus plus. I plus plus, this is called post increment. It means you're going to increment I, like we did before, but after the expression in which I appears is evaluated first. After you do the OR operation with A, then we will increment I. Does it print it's true? So we use I, we use the value, when we evaluate this OR, we use the value of I before it's incremented. I would be 0, I would be 0. So I is 0 when the OR operation is evaluated. Or 0 is interpreted as false. Since A is false, and I is 0, then the whole OR expression evaluates to false. So we do not print it as true. But after we use I in this OR operation, then we increment I, so I becomes 1. So we're going to print I equals 1. Does everybody get that? We don't print it's true, but we print I equals 1. Oh, we do print it's true, so it is true. Got it wrong.
We might have it else.
But it should skip over this. Did I compile it? No, I didn't compile it. It's not printing it's true. It just prints I equals 1. Well, look, if I were 1, this expression would be true. But see, I is not 1 when it's used in this OR operation because we're using the post increment, I plus plus. If we change that once again to what we had before, that's the pre-increment. That means increment I and then use I in the expression which in it appears. Now we will print I equals 1 as before, but we'll also print it's true. I'll call it the condition. The condition here in the if statement. The if statement condition is true. That'll be printed, and I will be 1. make this a post increment, I still becomes 1. But it's used, its previous value of 0 is used when evaluating the if condition. Does everyone get that? That's getting a little complicated, right? Now, ready for the next level of complexity? What if we do this? Oops. Yeah. Let's set A to true. What does this program print? It prints the if condition is true. What does it print here?
1.
It does not print 1. It prints 0. And the reason is the OR operation here, the compiler uses short circuiting. Let me tell you what short circuiting is. The code that's generated first evaluates the left-hand side of the OR expression. If the left-hand side of the OR expression evaluates to true, the right-hand side of that expression is skipped. It is not executed. So ++I is never run because the code, the compiler, short circuits. We call it short circuiting. Every language I know does this. So this will print I equals 0. Is that surprising? It's similar with AND. But the short circuiting works up differently. If the first argument evaluates to false, then the second argument is not evaluated. If the first argument to AND is false, there's no reason to evaluate the second argument, because whatever it evaluates to, the whole thing's false anyway. So let's just take a shortcut and say we're false. But that feature, that's built into all these languages. And you'll see that very tricky programmers, programmers that like to play with the language will rely on this feature, which may not be a good thing. But you see it especially in JavaScript. It's a language that I've been using a lot. You see programmers relying on short-circuiting heavily in their code. So as you read the code, you're not going to understand it unless you are fully aware of this short-circuiting behavior. Let's test our hypothesis here. So A is false, which means there's no reason to evaluate the right-hand side. So I will remain at 0. I remains at 0. Now, if A were true, then what happens? Well, if the left-hand side of the AND operator is true, we're not guaranteed that the total result will be true. Because if the right-hand side is false, then the expression, the AND expression, evaluates to false. So false dominates in an AND. True dominates in an OR operation. So here, A is true. So that means we can't short circuit to the answer. We can't jump to the answer and say, oh, the whole thing is true. We can't do that. We have to evaluate the right-hand side. So evaluating the right-hand side means we increment I. So I now becomes 1. Now there it is. And I think that's quite a bit on that. Excuse me. How to invoke or call functions, we talked about that. Boolean data type, conditional expressions. How to compare integers, floating point numbers, and strings. So let's suppose we have, two variables, I and j. We could do things like this. If I is less than j, then print I is less than j. I think that's enough, just I is less than j. So I is 0, j is 1. This uses this less than operator. This is a comparison operator. When you use a comparison operator to resolve this expression, I less than j, that expression evaluates to true or false. It has a Boolean data type. Whenever you use a comparison operator, you get a Boolean value as a result. That's why we use it in this if statement. How about this? J is 1 divided by 2. I'm just going to give you some tricky things here to think about. Does it print I is less than j? No, it doesn't. What does j equal? 0. Good. J is equal to 0. Let's make that a double. Make that a double. This is pretty tricky. What does j equal? Careful. 0. J is 0 because the division is integer division. That's an integer divided by another integer. We don't care about the assignment. Okay, that's done later. Let's think about assignment later. Just do division. Integer 1 divided by integer 2 is integer 0. And a 0 is assigned to j. I'm going to just comment this out here. So we're doing experiments, so we like to comment our code out. So j is 0. Oh, it's an error. Sorry. J is 0. All right, so what about this? J is 1 divided by 3. That's still 0, right? If we did this. Now j is not 0. At least one of the arguments to the division is not an integer, then we get floating point division. I think that's enough on that one. Loops, we talked quite a bit about loops already. Difference between floating point and integer division, we got that. How to round, adding 0.5. So here, if we want to let's call k an integer value. We're going to round j. So to round j to the nearest integer, we add a half. So j is 0.3333, like that. We want to round it to an integer. What does j become? 0.333 rounded to an integer should be what? 0. Yeah, it's closer to 0. What happens if we had 2/3? So j rounded to an integer now should be 1. There it is. I think that's... Any questions on this material I covered today? I went over it pretty quickly. Are there any questions about problems that you've been working on, let's say from any of these labs or the sample exam? I want to remind everybody it's never too early to start practicing for the exam. You look at this code. You have to be able to read that code and write down in the exam what does this code output to the console? What does it print? You need to be able to analyze this. So you should start practicing these now. Of course, this is also a lab. Those problems are also part of this lab as well. Right here, exercise 2. It looks just like an exam. And you'll see some of these problems in here use, this is floating point division, this is integer division. It's a simple test of your understanding of the difference between floating point and integer division. Yeah?
So that one, since the first part is 1 divided by 2, that'll be 0.
Yeah, this is 0.
Okay.
That's 0 because it's integer 1 divided by integer 2. The context, it's the left-hand side, right-hand side are both integers. We're going to have integer division. So we'll have a result that's an integer without rounding. If you want rounding, you have to add 0.5. This division produces 0.5 because the right-hand side of that division expression is a floating point value. When we use a decimal point, even though it's 0.0, it's still interpreted as a floating point value.
Can you go over the one that you went over last time? I think it was number 3, I think.
3?
That was trying to do your reasoning, how you minus it 11, you get 88. but I kept coming up to 100 now.
Oh, this one here?
How far?
Yeah.
Let's do this one. This is one of the harder ones. Before we run it, let's analyze it. So I is initialized to 11. Then we enter this loop. Depends on the value of I. As long as I is less than or equal to 99, we execute the body of the loop. So what the body of the loop does, it adds 3 to I. So it's going, as the loop runs, it's just going to keep adding 3. So we want to know how many 3s is it going to add until it quits. So it's going to add some number of 3s. So let's do an approximate solution. I starts at 11, and it has to go up 88 to hit 99. So how many 3s are in 88? Anybody know? Roughly. Let's see, how many 3s are in 90? 30. Okay. Let's suppose that we add 30 3s to I. So 33s is 90. So if we run the loop 30 times, we're going to add, if we run the loop 30 times, we're going to add 90 to I. So I would become 101. So when I becomes 101, the loop condition is false. But maybe that's not the right answer. So it might print 101 here. Well, maybe we went too far. Let's try 29 3s. Suppose the loop runs 29 times. We add 29 3s. So that's 87. Let's suppose we run 29 times. We add 87 to I. What's 11 plus 87?
98.
98. So when I is 98, so the 29th 3 that we add, I becomes 98. And we check the loop condition. Well, 98 is less than 99. So we're going to do the loop again. So we're going to add 3 to 98. We're going to get 101. After we get 101, we're going to check the loop condition again. The loop condition is now false. That means we don't add 3 anymore. We're done. I is at 101. So we print 101. And you got something different?
I kept getting 100.
100.
Yeah, I don't.
You're just off by 1. What? Non-ASCII characters not allowed. Look at this. You see this? Oh, here's the problem. This is a PDF document, and I copied and pasted from that. I have to do this every class. And they're, behind the scenes, the characters that appear inside documents, like PDF documents, Word documents, C++ files, they are represented by numbers. And there's different representations. And those are called character sets, the different types of character sets. And the C++ language relies on this ASCII character set. And it's saying, hey, that semicolon is a non-ASCII character. I can't deal with that. But, the browser doesn't have any trouble rendering that as a semicolon. And when I pasted it into the program, this VI that I'm using didn't have any trouble with it either. It just took the character data that it had, and internally, a semicolon is a number. But it's a number from a different character set. Oops, sorry. We are there. Just going to delete that. And then I'll add one back in. Actually, there's a lot of errors. This, the I equals I plus 3, you see that? So I just fixed this one, so that should disappear. Let's see if that works. I can't read that. It does work. Now let's fix the one in this expression and this expression. I did it. See that? Think you can debug those problems in the future? Because remember, internally, behind the scenes, characters are represented by numbers. And there's many different ways to do that representation. And the problem comes from when computers are originally created. They represented characters with single bytes, which only take on 256 distinct values. So a single byte, you can only have an alphabet that has at most 256 characters, including punctuation and mathematical symbols and other symbols that you might need, and white space, spaces, and tabs, and all that. So we were limited to 256 from the early days of computers. But when other languages started being used in the context of computation, it wasn't enough states of a byte to represent all the different characters from all the different languages. So people had to change the character set. So there's a character set for German, a character set for French, and a character set for Greek. So there's still single byte values that represent characters, but they represent different characters from different languages. And then you have the problem of languages that have more than 256 characters, like Chinese, for instance. That cannot be represented with a single, those characters cannot be represented with single bytes. So you need a multi-byte character sets. And then various conventions are created to enable multi-byte character set representations. Some representations use 2 bytes. Some representations use multiple bytes. In other words, a string in a language like Chinese is represented by a string of values that are, some of them 1 byte long, some of them 2 bytes long, some of them 3 bytes long, maybe even 4 bytes long. So those are variable length representations. So it gets really, I got to tell you, it gets very, very messy at some point. But we're not going to get into the details in this class other than recognizing that it is an issue and it's something that you have to pay attention to. So we compiled this program. Now let's run it. It says 101. I'll just add this for make it easier to read. So you need to go back and try that thinking process all over again and see if you can get the 101 this time. And also, it's not just that problem. There's other problems that are listed here that are similar, so you have other chances to try different versions of this problem. I think, is that enough for today? Actually, I need to run somewhere, so I'm going to call it quits today. And we'll see everybody on Monday. Please start studying for this exam that's coming up.
Yeah. I can do it. Sorry, I'm getting one time.